Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. As always, our mission impossible is simply to convert some of that hate energy to love energy. Much better to love than to hate. I think you'll all agree. As your screen indicates, like it or not, math really did take us from the Stone Age to the Space Age. Now let's get down to some serious math. All we're doing here is, this is video 2 of the Exponent series, and we're continuing to deal with exponent laws. And as your screen indicates, the next law we're going to be talking about is the Quotient Difference Law for exponents. So the Quotient Difference Law goes like this. If you have a to the power b over a to the power c, notice this is like a fraction of 2 powers. Okay, fraction of 2 powers. You'll notice that the base is common. The common base is a. And when that occurs, that means you've got BA's on top and you've got CA's on the bottom. What happens is that the CA's on the bottom will cancel out with C of these BA's on top. Again, you have BA's on top, CA's on the bottom. That's what this means, because B and C are both frequency counts. The CA's on the bottom will cancel out C of these BA's on top. When that happens, we get the result becomes a to the power b minus c. So the minus c indicates that the CA's on the bottom are canceling out C of the B's on top. Or, sorry, are canceling out, C of the BA's on top. Okay, that's kind of, anyway, the examples will illustrate exactly what I'm talking about. The abbreviation will be QDL for Quotient Difference Law. And let's look at the examples. Example 1, it says 2 to the power 5 over 2 to the power 3. Again, this indicates that there are 5 2's on top and 3 2's on the bottom. Okay, these 3 2's on the bottom will cancel out 3 2's on top, and what remains is 2. There are only 2 2's left. To do that quickly, we use the Quotient Difference Law. It becomes 2 to the power 5 minus 3, which is 2 to the power 2, which is 4. So the Quotient Difference Law is really a cancellation law. Okay, so whenever you see something of the form b minus a, what you're really doing is canceling. Let's look at example 2 down here. We have 3 to the power 5 over 3 to the power 1. The Quotient Difference Law says that if the common base, or if the base is common, which in this case it is, all you do is subtract the exponents. You take the top exponent, which is 5, and subtract the bottom one. And we get 3 to the power 5 minus 1, which is 3 to the power 4, which is 81. The Quotient Difference Law also works when the base is a fraction. A fractional base is called a rational base. So when the base is fractional, same law applies. You've got, how many 2/3 do you have on top? You have 7. How many 2/3 do you have on the bottom? You have 5. How many 2/3 do you wind up having after you do the cancellation? Of course, you're going to wind up with 2 of them on top. So using the Quotient Difference Law, this becomes 2/3 to the power 7 minus 5. That would be 7 minus 5. And of course, 7 minus 5 is 2. And we get 2/3 to the power 2. And of course, that can be written as 2/3 dot 2/3. And when we multiply fractions together, you do 2.2, which is 4, and 3.3, which is 9. And 4 over 9 is a proper fraction, and it's in reduced form, so we're done. So we'll go on to the next slide. We're going to be doing some questions that both involve the product sum law and the Quotient Difference Law simultaneously, because these laws can all be applied simultaneously, which means that the simplification process can be made very expedient. If we look at this, we identify a single cluster. There are no pluses or minuses. We don't see anything over here indicating that there is more than one cluster. They're all dots on top, all dots on the bottom. We have a fraction that constitutes a single cluster. If we look at this cluster carefully, the only base we see is base 2. So we identify a single cluster, the common base is 2, and we can certainly apply the product sum law and the quotient difference law simultaneously and within that cluster. So this is how we do it. We identified that the base was 2. What we do is scan the numerators first and collect all the exponents. We get a 3 plus 4 plus 5. And there it is, 3 plus 4 plus 5. Because these exponents over here are on the bottom or belong to the denominator, the quotient difference law kicks in, and we get a minus 2 minus 1. So 3 plus 4 plus 5 is essentially the product sum law, and then minus 2 minus 1 is the quotient difference law. And we can use those two laws simultaneously. And then all we do is simplify the exponent, the integer string in the exponent here, and we get 2 to the power 12 minus 3, and of course 12 minus 3 is just 9, and 2 to the power 9, you can evaluate that manually, or you can use the power button on your calculator to get 512. Let's look at Q2 over here. Again, we're going to be using the product sum law and quotient difference law, and the question is very similar to the one we just finished doing. We identify a single cluster here because they're all dots on top and they're dots on the bottom. So we have a product string on top and a product string on the bottom. We identify the common base as 3. So to summarize, we have a single cluster, the common base is 3, and we're allowed to use the product sum and the quotient difference laws simultaneously. So you open up base 3 on the bottom right here, and what we're going to do is collect all the exponents. On top we get a 4 plus 5 plus 2 plus 7, and on the bottom we get 11 and 4, but because they're on the bottom they become 11 minus 4. And then we can simplify the integer string, and we get 3 to the power 18 minus 15, and of course that gives you 3 to the power 3, and 3 to the power 3 we can evaluate the power to get 27. Okay, let's go on to the next slide. Let's look at Q3 here. We have 2 to the power 4 dot 3 to the power 5 dot 2 to the power 7 dot 3 to the power 3 over 2 to the power 3 times 3 to the power 4. Again, we identify a single cluster because we have a product string on top and a product string on the bottom. We look for common bases. The common bases are 2 and 3. So again, we identify a single cluster and the common bases are 2 and 3, and we can certainly apply the product sum law within that cluster. The product sum law and the quotient difference law simultaneously within the cluster. And the way you do it is by considering each base in turn. We start off with base 2, and we collect all the exponents. We get a 4 plus 7 on top, so we drop a 4 plus 7 there. We get 3 on the bottom, becomes minus 3. We're done with base 2. Then we can go on to base 3. We scan the numerator. We pick up a 5 plus 3. That's the product sum law. And we drop it in, and on the bottom, 4 becomes minus 4. That's the quotient difference law. And now we're going to simplify this string, and you get 11 minus 3 there. Simplifying that, you get 8 minus 4. Continuing to simplify, you get 2 to the power 8, dot 3 to the power 4. You can evaluate each power. 2 to the power 8 is 256, and 3 to the power 4 is 81. And again, this product you can do on the calculator, and the final answer will be 20736. And second problem, identical to the one we just finished doing, just a little bit more practice. Again, we get one cluster. We see that we have one cluster. You have a product string on top, product string on the bottom. identify the common bases as 3 and 7, and we can apply the product sum law and the quotient difference law simultaneously for each base. So we'll start off with the smallest base, which is 3, and we scan the numerator. We pick up a 5 plus 6, drop it in, and on the bottom 3 becomes minus 3. The second base is 7, so we open up base 7 here. We scan the numerator for exponents, and we pick up a 3 plus 4, drop it in, scan the denominator, and put a minus 5. Again, we have a little integer string here, integer string there, and 5 plus 6 is 11, and then we have a minus 3, and 3 plus 4 is 7, and then we have minus 5. Continuing to simplify, we wind up getting 3 to the power 8 dot 7 to the power 2. Again, we evaluate each power. 3 to the power 8 is 6561, and 7 to the power 2 is 49. At the end, you evaluate this product. Of course, you're going to do it on your calculator, and you wind up getting 321,489. Let's go on to the next slide. Over here, this time we have a separator. We have a minus sign separating two clusters. The first cluster contains only base 2. The second cluster contains only base 3. So again, we identify two clusters. The common bases are 2 and 3, but the 2 applies to the first cluster and the 3 applies to the second cluster. And we're going to be applying the product sum law and quotient difference law again simultaneously for each cluster in turn. Again, you cannot apply the product sum law and the quotient difference law between clusters, only within a single cluster. So this is the base 2 cluster over here. We put down base 2. We pick up a 2 plus 5 minus 1 minus 3. And then we drop the minus sign down. We put down base 3. And for the exponents, we pick up a 4 plus 2 plus 1 minus 3 minus 0. Now we have an integer string. We just simplify to get 7 minus 4. And over here we simplify to get a 7 minus 3. Again, the clusters cannot interact, okay, until the very end. So we continue to simplify each cluster. You get 2 to the power 3 minus 3 to the power 4. 2 to the power 3 is 8. 3 to the power 4 is 81. At the end, you have 8 good guys, 81 bad guys. The bad guys win, and you do large minus small. And the final result is minus 73. Okay, let's go on to the next slide. Same sort of idea over here. This is a little bit more complicated. We identify 3 separate clusters. The separators for the clusters are the minus sign and the plus sign. The first cluster involves base 2, base 3. Second cluster involves base 3, base 5. Third cluster involves base 2, base 5. Again, we identify 3 clusters. The common bases right across the board are 2, 3, and 5 that we're going to be dealing with. And we're going to apply the product sum law and the quotient difference law simultaneously for each cluster. So we focus on one cluster at a time. If we look at the first cluster, we can open up a base 2. And then we pick up a 4 plus 7 and minus 9. 4 plus 7 minus 9. Then we use a dot because you need to concatenate. And there's always a dot in between. Within a cluster, it has to be a dot. The next base is base 3. We scan the numerator, we pick up a 5, and then a 2 becomes minus 2. Then we go on to the second cluster. Drop the minus sign down. Open up base 3. Scan the top. We pick up a 2 plus 5, and then minus 4. So 2 plus 5 minus 4. And then a dot. Put down base 5. We scan the numerator for base 5. You only pick up a 4. And the denominator, you pick up a 2, becomes minus 2. And then the separator, which is a plus sign. And over here, we open up base 2 to start. We scan for the exponents. We get a 7 plus 4, and then minus 10. 7 plus 4 minus 10. Then a dot. The second base is 5. We scan. We get a 7 minus 5. And now we simplify each exponent string. Let's call these exponent strings, okay? That's a good name for them. Anyway, starting off with the first cluster, we get 2 to the power 11 minus 9, dot 3 to the power 3, minus 3 to the power 7 minus 4, dot 5 to the power 2, plus 2 to the power of 11 minus 10, dot 5 to the power 2. We continue to simplify the exponents. We get 2 to the power 2, dot 3 to the power 3. And then minus, this becomes 3 to the power 3, dot 5 to the power 2. Plus, this becomes 2 to the power 1, dot 5 to the power 2. Slowly but surely, we're getting there. Now you evaluate each power for each cluster. We get 2 to the power 2 is 4, 3 to the power 3 is 27, drop the minus sign down, 3 to the power 3 is 27, 5 to the power 2 is 25, drop the plus sign down, 2 to the power 1 is 2, 5 to the power 2 is 25. And then we perform these products for each cluster. We get a 4.27 is 108, and minus 27.25 is minus 675, and plus 2.25 is plus 50. So again, we've got some good guys and some bad guys at the end. And we have 158 good guys, 675 bad guys. The bad guys win, and you do large minus small. So we get minus 517 at the end. Okay, let's go on to the next slide. And you know what? We're going to call it quits for now. So thank you all for viewing this video. Stay tuned for many more to come. If you liked the video, please give us a like and subscribe to our channel. If not, tell us how to improve it, please. Over and out from MathLab Tutorials in Toronto.